Imagine you've just spent like 8 hours in a muddy trench splicing a 288 core of fiber optic cable.
Oh, sounds miserable.
Right. Your back aches, the daylight is fading, and you finally hook up your OTDR to run that final certification test.
The moment of truth.
Exactly. And the results come back, and your insertion loss is just failing across the board.
Ouch.
Yeah, you are facing hours of rework. So do you blame the technician, the glass, or, the machine? Today, we are looking at the real cost of hardware in the high-stakes world of professional fiber optic installation.
It's a huge topic.
It really is. Okay, let's unpack this. We have an incredibly detailed stack of sources today, including some product specification sheets from Contractor Essentials, and this very illuminating technical breakdown by Jeremy White over at TMG.
Great article.
Yeah, really good stuff.
Yeah.
Our mission for you today is not just to talk about what fusion splicing is. I mean, if you were in this industry, you already know the stakes.
Right.
But we want to evaluate the genuine return on investment between top-tier and value-engineered equipment.
Which is something a lot of people struggle to balance.
Exactly. So to do that, we are analyzing a tale of two machines. We've got the Tier 1 Sumitomo Type BE72C plus Parkar, which comes in at just over $11,000.
Yep.
And the value-engineered Tumtec FST-83A, which sits around $4,000.
That price gap is really the elephant in the room for any contractor looking to, upgrade their fleet or start a new operation.
It's a massive difference.
It is. And comparing these two specific models highlights precisely what you are paying for when physical tolerances are measured in fractions of a micron.
Fractions of a micron, yeah.
We are going to guide you through the raw data, the environmental engineering, and the total cost of ownership to show you how a machine capabilities directly dictate a network's long-term profitability.
Well, let's start with the fundamental mechanics of the job because, the hardware only matters in the context of the standard it has to meet, right? Fusion splicing isn't just about sticking two pieces of glass together. The industry standard for insertion loss, which is just the amount of signal lost at the splice point, is fiercely strict.
Very strict.
We are talking about hitting like 0.01 to 0.02 decibels of loss on a single mode fiber.
Which is incredibly tiny.
Yeah, it's like trying to perfectly super glue two microscopic glass straws together end to end, but without accidentally blocking the hole inside.
That is a great way to visualize it.
But, I have to push back on industry conventions for a second here.
Okay, go for it.
If creating this permanent microscopic weld in a dirty trench is so prone to failure and requires such expensive equipment, why hasn't the industry moved toward high-grade, ruggedized plug-in connectors?
Oh, I see where you're going.
Right. Like you terminate the ends in a controlled factory and the field tech just clicks them together like a heavy-duty USB cable. If a port fails, you just unplug it and swap it.
It is a totally tempting proposition from a purely labor-saving perspective, I'll give you that. But the physics of light transmission over distance ruthlessly shut that idea down.
Really? How so?
Well, when you are building a long-haul backbone or a dense fiber-to-the-home rollout, every mechanical connection introduces an air gap.
Even the factory-made ones?
Even those, no matter how tightly they are manufactured. Plug-in connectors are notoriously vulnerable to microscopic dust ingress, temperature expansion, and physical vibration.
Oh, sure. I guess a trench isn't exactly a clean room.
Right. And over time, those mechanical connections degrade, which causes intermittent optical faults and signal reflection. Essentially, the light bounces back toward the source instead of continuing down the line.
Okay, so it's about the link budget then.
Exactly.
Because when you are pushing high bandwidth traffic over dozens of kilometers, a series of, say, 0.2 decibel losses from mechanical connectors would compound and eventually just kill the signal entirely.
You've got it. Which is why permanent fusion splicing remains the absolute standard. Melting the two cores into a single, continuous strand of glass is literally the only way to preserve signal integrity across massive networks.
Gotcha.
And to hit that 0.01 decibel standard, the alignment of those cores prior to the arc has to be virtually flawless.
Which brings us to the technology separating our two machines. Let's look at how two drastically different price points attempt to hit that exact same ultra-strict alignment standard.
Right, let's look at the gear.
First up, the Sumitomo Type E72C Plus Hughes. As a Tier 1 standard machine, it relies on real-time 3D high-definition core alignment with 380 times single-axis magnification.
Impressive specs.
Yeah. And then on the other side of the desk, the Tumtec FST-83A uses an active V-groove system, paired with what they call a digital analysis core alignment system, or DACAS.
DACAS, yeah.
And that boasts up to 500 times magnification. So wait, the Tumtec actually has higher magnification, but the physical alignment mechanism is totally different.
Yes, and the mechanism is where the cost difference truly lives. What's fascinating here is how the Tumtec uses active V grooves.
Okay, how does that work?
Inside the machine, there are tiny physical motorized blocks shaped like a V. The machine places the fiber into these grooves and physically nudges the outer layer of the glass, the cladding, up, down, left, and right, until the software determines the fibers are aligned.
So it's physically moving the whole strand.
Right. But it relies on the assumption that if the outer cladding is perfectly matched, the inner core carrying the light must also be matched.
But manufacturing isn't always perfect, right? Like, sometimes the core isn't perfectly dead center inside the cladding.
Exactly, and that is the absolute limitation of cladding alignment.
Okay.
The Sumitomo, however, uses true core alignment. Its cameras look past the outer cladding, focusing directly on the microscopic core itself.
Oh, wow.
Yeah, so it aligns the actual light pathways regardless of any concentricity errors in the outer glass.
Yeah.
But it doesn't stop there.
There's more.
Yeah, the Sumitomo takes that visual data a step further using its nanotune technology. This isn't just digital alignment. It incorporates real-time neural network algorithms.
Okay, I have to stop you there because, AI gets thrown around as a buzzword a lot lately.
It really does.
How does an algorithm actually physically improve a weld on a piece of glass? Because the tech still has to manually strip the fiber, clean it, and score it with a cleaver, right?
Right, the manual prep is still there.
And a cleave has to be a perfectly flat 90-degree break. If a technician is rushing and makes a bad, jagged cut, the machine is still working with broken glass. How does an algorithm fix physical damage?
Well, the algorithm doesn't fix the physical glass. It alters the plasma arc to compensate for it.
Wait, really?
Yes. When the Sumitomo's cameras look at the freshly cleaved end face, edge detection software maps the topography of the cut. It calculates the exact angle of the break.
Okay.
If the cleave is imperfect, say a 3-degree angle instead of perfectly flat, the neural network cross-references that specific defect against thousands of stored splice profiles.
Oh, that is wild.
In milliseconds, it automatically alters the duration, shape, and intensity of the electric arc. It essentially melts the glass slightly differently to absorb that 3-degree error and force a seamless fusion.
Okay, so it's the difference between a microwave and a high-end smart oven.
I like that.
Like, the Tumtec is a microwave. You put the glass in, the active V-groove lines it up, and it fires a standard preset arc profile. If you put a bad cut in, you get a bad splice out.
Yep, pretty much.
But the Sumitomo is a smart oven. It looks at the thickness and temperature of the meat, realizes it's an uneven cut, and automatically adjusts the broiler elements so the steak cooks perfectly anyway.
That is a highly accurate way to look at it. The Tumtec places all the responsibility for a clean cleave squarely on the manual discipline of the technician.
Right.
The Sumitomo, though, actively serves as a safety net for human error and environmental fluctuations.
Now, with the machine doing all that computational heavy lifting on the back end, you'd think it would slow the whole process down.
You would think so. But when you look at the raw speed metrics, it's the exact opposite. And here's where it gets really interesting, because this is where theoretical engineering translates into raw job site productivity.
Let's hear the numbers.
The Sumitomo executes a splice in just 5 seconds when set to single-mode quick mode. The Tumtec takes between 6 and 8 seconds.
I mean, 3 seconds of processing time is a negligible difference. If you are just splicing a single broken drop wire outside a residential home, you honestly won't even notice it.
Well, the splice itself isn't the real bottleneck, is it?
No, it's not.
Once that glass is fused, it is incredibly fragile. The technician has to slide a protective plastic sleeve over the bare joint and bake it in a built-in oven on the machine to shrink it down, creating a rigid seal.
The heat shrink process.
Yeah.
Right.
Now, the Tumtec features a single oven that takes 15 to 20 seconds to run a heat cycle. The Sumitomo features fully optimized dual independent ovens, and its heat shrink time is only 8 to 9 seconds.
And those dual ovens completely alter the operational workflow.
Really? How much of a difference does it make?
A massive one. When a technician is working inside a massive enclosure, they establish a rhythm. With the Sumitomo, you splice fiber pair number 1, drop it into oven A, and hit heat.
Okay.
While oven A is baking, you immediately prep and splice fiber pair number 2. By the time pair 2 is fused, oven A pops open, finish. You move pair 2 into oven B.
Oh, I see.
It creates a continuous, uninterrupted assembly line.
So to put this in perspective for the listener, If I'm an independent contractor doing local, low-density work, maybe hooking up 3 or 4 homes in a day, that single oven on the Tumtec is perfectly adequate.
Absolutely.
The extra 10 seconds of waiting isn't going to impact my bottom line. But if I'm contracted on a major carrier backbone rollout, splicing 288 core cables day in and day out, that single oven becomes a massive choke point.
Exactly.
Over the course of a week, waiting 20 seconds for every single sleeve to bake turns into hours of last labor.
You are literally paying the wages of a highly skilled technician to sit and watch plastic melt.
Wow, yeah. That adds up fast.
It does. The dual oven setup on the Sumitomo eliminates that dead time, fundamentally changing the daily labor cost calculation on high-volume sites.
But wait, running 2 heating elements continuously while simultaneously powering an AI-driven camera system has to draw a phenomenal amount of power.
It's a heavy load for sure.
How does a portable unit sustain that kind of draw without dying halfway through a dupe trench enclosure? Let's look at the battery math for a second.
Sure.
The Tumtec utilizes a brute force approach, offering a massive 5,200 milliamp hour battery. Their specs indicate this yields around 280 splicing and heating cycles.
That's a solid number.
It is. But the Sumitomo, despite powering dual ovens and high-end processing, achieves 300 cycles.
And the crucial metric to attach to those cycle counts is the physical weight of the machines.
Oh, good point.
The Sumitomo achieves those 300 cycles while keeping the total weight of the unit down to just 2.2 kilograms.
Wow. I've lifted laptops heavier than that.
Right. It is a triumph of power management engineering. When you are carrying this gear up telephone poles, balancing it in bucket trucks, or dragging it through cramped basements, a lightweight machine directly reduces physical fatigue.
That makes a ton of sense.
The Tumtec kit, while highly durable, is definitely bulkier. The shipping weight is listed at 8.3 kilograms, meaning the unit itself and its housing carry significantly more mass. Sumitomo prioritized power efficiency to keep the weight minimal without sacrificing stamina.
Well, since we are talking about carrying this equipment out of the site, we need to transition from looking at just the machine to looking at the entire ecosystem you are buying.
Let's talk unboxing.
Yeah. When you purchase one of these from Contractor Essentials, you are getting a full kit. Evaluating the included accessories reveals a stark philosophical difference in who these products are meant for and their setup efficiency.
The accessory lists clearly define the target demographic for each machine.
So let's break down the premium Sumitomo kit first. You receive the splicer, a hard transit case, a rechargeable battery, a cleaver, a standard fiber optic stripper, a cooling tray, spare electrodes, power leads, and the manual.
Basically the essentials.
Right. It's streamlined. It provides exactly what you need to operate the machine itself and nothing more. Then you look at the Tumtec kit.
And that one is packed.
Oh, yeah.
Big
You
gap.
get all the standard hardware, but you also get a CFS3 stripper, a specific cable stripper, and an alcohol dispenser for cleaning the fiber.
Very handy.
Most importantly, it includes an OHS compliance triber, CLV X6 cleaver. This specific cleaver features a built-in waste bin that automatically catches the microscopic glass shards you cut off the fiber.
Which is a fantastic feature.
Yeah, and the Contractor Essentials listing explicitly notes this cleaver is not normally a part of this kit.
Including that specific cleaver, along with the alcohol dispenser and stripping tools, is a highly deliberate packaging choice aimed at maximizing immediate professional value.
So they're really trying to sweeten the deal.
Exactly. The Tumtec is essentially a business in a box. If you are a new contractor just starting your independent operation, you need every single piece of the prep workflow on day one.
True.
You can't splice without alcohol to wipe the glass, and capturing glass shards is critical for occupational health and safety compliance on modern job sites.
So why doesn't the $11,000 kit include the alcohol pump and the fancy waste bin cleaver? You'd think the premium price tag would get you all the premium accessories.
Honestly. Because Tier 1 buyers don't want them.
Really?
Yeah. A seasoned telecommunications veteran purchasing a Sumitomo likely already owns highly customized premium hand tools.
Oh, that makes sense.
They have a preferred brand of strippers they've used for a decade, custom cleaning cassettes, and high-end standalone cleavers. If Sumitomo bundled a bunch of generic starter tools into the kit, they would just end up sitting in a drawer, adding unnecessary cost to an already expensive package.
Okay, that makes perfect sense. The veteran just wants the high-performance engine. The newcomer needs the whole car, down to the floor mats. But regardless of your experience level, once you unbox these kits, you have to take them out into the real world. Fiber splicing rarely happens in a pristine, climate-controlled laboratory.
Very rarely.
We've talked about the internal tech, but How do these units handle the environmental realities of fieldwork?
Well, if we connect this to the bigger picture of network reliability, environmental ruggedness is just as critical as alignment technology.
How so?
The Sumitomo is heavily certified in this regard. It holds an IPIce2 rating for water protection, meaning it can withstand dripping water or light rain, and an IP5X rating for dust protection.
Which is huge.
Absolutely vital if you are working near a gravel road or up in a dry, dusty ceiling cavity.
It also claims a 76-centimeter drop rating on 5 faces and operation in temperatures up to 50 degrees Celsius.
Those are serious specs.
They are. But the spec that really jumped out to me was the altitude rating. It claims to function perfectly at up to 6,000 meters above sea level. I have to ask, who is splicing fiber optic cables at 6,000 meters? That is higher than Mount Everest Base Camp. Is there a massive market for gigabit internet at the summit of Kilimanjaro?
You know, while there are certainly high-altitude installations in mountainous regions, the 6,000-meter specification isn't really about climbing mountains.
No. Then what's it for?
It is a flex of extreme engineering margins. Altitude dramatically affects air density.
Oh, right.
A fusion splicer relies on generating an electric plasma arc across a microscopic gap in the air. If the air density changes, the resistance changes, and the shape and heat of the plasma arc become erratic.
So by over-engineering the arc control system to maintain a perfect stable plasma field in the freezing thin air of 6,000 meters, they are effectively guaranteeing that the arc will be flawlessly stable on a hot, humid day at sea level.
Precisely. Extreme specifications act as an operational buffer. If the internal components can survive a 50-degree Celsius heat wave or perfectly regulate voltage in thin air, it guarantees extreme reliability against the everyday bumps, dust, and temperature swings of a normal job site.
That is fascinating.
It prevents the machine from shutting down when conditions get slightly uncomfortable.
Which feeds directly into the most critical concept in Jeremy White's TMG article, total cost of ownership.
Yes. TCO is everything.
The true cost of a fusion splicer isn't just the sticker price. TCO is the purchase price, plus rework costs, plus downtime, minus the resale value.
That's the formula.
Let's walk through a real-world scenario rework math. Let's say you buy a budget machine, and because it lacks the nanotune AI to fix a slightly bad cleave, you fail an OTDR test on a 48 fiber enclosure.
A nightmare scenario.
To fix that, you have to roll a bucket truck back out to the site.
Right, and you are paying for the fuel, the hourly wage of 2 technicians, the safety gear, and the time spent physically digging up the pit or opening the aerial enclosure just to get back to the glass.
Just to get to it.
You could easily burn 4 to 5 hours of labor fixing one bad splice.
And when you factor in the opportunity cost of those technicians not being on a new paying job, that single truck roll could cost $1,000. If a premium machine prevents just 7 or 8 of those rework scenarios over a year through AI correction and environmental stability, that $7,000 price difference vanishes.
Completely vanishes. And minimizing downtime extends beyond just the physical splicing. The Sumitomo ecosystem includes wireless LAN connectivity, linking the splicer to a smartphone app called SumiCloud.
Oh, right.
For large fleet operators, this is a massive operational advantage. It offers remote asset tracking, allowing managers to see exactly where their high-value equipment is deployed.
It's essentially a Wi-Fi-connected fleet management device.
It is. It monitors machine health and sends maintenance alerts to the technicians' phones, telling them exactly when it is time to change the electrodes based on arc counts, preventing poor splices before they happen.
That's incredibly smart.
Furthermore, it automates compliance reporting. The machine logs the specific data of every single splice time, location, and estimated loss and generates a report.
Well, that saves so much paperwork.
Exactly. When you are dealing with strict service level targets for national carriers like the NBN or meeting Australian Communications and Media Authority standards, having automated, unalterable proof of your splice quality prevents disputes and ensures contractors get paid faster.
But, you know, a solo contractor doing internal building maintenance doesn't necessarily need a cloud-connected fleet management system, right?
No, they probably don't.
They just need a machine that turns on and fuses glass reliably.
Which is exactly why the value-engineered Tumtec models remain incredibly popular. They lower the barrier to entry, allowing small businesses to compete for contracts without taking on massive debt.
Makes sense.
Furthermore, large civil fleets frequently buy these sub-$5,000 units to keep in the truck as emergency backups.
Oh, as a spare.
Yeah. If your primary machine requires calibration or maintenance, deploying a Tumtec keeps the crew operational instead of sending them home for the day.
Okay, so we've navigated the physics of light loss, the difference between active V-grooves and AI-driven core alignment, the operational bottlenecks of single versus dual ovens, and the hidden math of total cost of ownership.
We covered a lot of ground.
We really did. Let's distill all of this down and help the beginner make a clear, evidence-based decision between these two specific kits.
Okay. If your contracts involve high-density ribbon work where you are splicing multiple fibers simultaneously or major carrier backbones, the Sumitomo Type FST-82A Plus is the logical choice.
Yeah.
The dual oven speed, the nanotune automated quality assurance, and the ruggedized environmental margins will actively drive down your labor and rework costs. The machine is designed to absorb human error and maintain a continuous, high-volume assembly line.
However, if you are an independent contractor, if your primary focus is general commercial building maintenance, localized drop repairs, or you simply need a dependable daily workhorse to launch your business, the Tumtec FST-83A provides immense professional value.
It really does.
It will absolutely hit the strict 0.02 decibel insertion loss standards required by the industry, provided you, the technician, bring the manual skill and discipline to the preparation and cleaving process.
That's the key.
And the business-in-a-box accessory kit means you can start generating revenue the day you open the case.
It fundamentally comes down to whether you want to pay for the machine to manage the variables or if you trust your technicians to manage the variables themselves.
So what does this all mean for you, the listener? It means that in modern telecommunications, splicer quality sets the ceiling on overall network reliability.
Perfectly said.
You can buy the most heavily armored, ultra-pure fiber optic cable on the planet,
Yeah.
but if the machine melting the joints together lacks the processing power or physical precision to perfectly align those microscopic cores, the entire network will bottleneck at the splice point.
Right.
The physical infrastructure of our digital world is entirely dependent on the integrity of its weakest microscopic joints.
It's crazy to think about it that way.
It really is. We've covered a massive amount of technical ground today, but we want to leave you with one final, slightly provocative thought to mull over.
Always good to end on a question.
We spent a lot of time analyzing the Sumitomo's nanotune AI technology, specifically how it actively compensates for a technician's sloppy physical work, like a poorly angled manual cleave.
Yeah.
As edge detection algorithms and neural networks get faster and better at anticipating and fixing our physical mistakes in real time, are we slowly erasing the traditional manual craft of the telecommunications technician?
Oh, that's a deep question.
Right. In 10 years, as these machines become increasingly autonomous, will a field technician even know how to manually interpret a bad cleave or compensate for high altitude? Or will they be entirely dependent on a localized neural network to do the thinking for them?
It's the eternal tension between automation and human skill.
Playing out right now on a microscopic scale. Until next time, keep digging into the details.